I'm Nicola Turini from University of Siena. I've been at the beginning of PPS the deputy project manager. Then I was responsible for the timing detectors. In this moment, I am just a professor. I was working before in the totem experiment, and then the totem experiment evolved into a part of the CMS experiment, which is the so-called PPS, Precision Proton Spectrometer. While totem was running in special runs with low luminosity, the PPS is running every day with high luminosity. If you look straight at 220 meters from here, there is the heart of CMS. The proton travels up here, pass through these two pipes. This is the so-called arm 5-6 because it goes from 0.5 CMS to 0.6. When protons interact inside CMS, most of the time they destroy, and CMS looks at the debris. But sometimes the protons have an interaction and they remain intact and continues to travel, but they lose energy. By losing energy, they create a new matter inside the center of CMS. The magnets are made on purpose to keep the protons with the largest energy into the beam, while when they lose some energy, they escape on one side. So we put special detectors here that measure the position of the tracks of these protons that have escaped sideways because of the magnets. We study the interaction light by light. It's something that is completely new, unknown, but also the fact that we measure the protons coming out from the interaction and we can measure the energy of these protons very precisely, we can know exactly the kinematics of the production vertex. Here, since the proton remains intact, we know exactly everything. So what we are doing now mostly is beyond standard model searches. We search for dark matter because knowing the kinematics in the center, if something visible is escaping, we can measure exactly their kinematics, their mass and everything. And so we have one paper that we did already in which we search some invisible mass that recoils to a Z, and now we are doing an analysis in which we have an Higgs boson that is recoiling towards an invisible. So this is pure beyond standard model studies. These are called Roman pots because the first group that did this kind of detectors were a group from Rome. If you look inside, it looks like a pot where you can cook pasta. Of course, the technology has evolved. For example, you have vacuum here, the pot goes in, so you can think that it's sucked inside. On the bottom, you don't see it, but there is another vacuum chamber that compensates the vacuum just to have it perfectly in balance. So here is a bellow that allows to close by and go back far from the center of the beam. The detectors are put here like this, and when we insert the pots, they go up to 1.5 millimeters to the beam. So you have to imagine that the beam is like this and the detectors just almost touch it. And during the alignment, in fact, we touch it. They send just 3 bunches out of 2,800. And we go in, we touch it, and we go back. And so we decide where is the position of the beam and how to get close when we have the normal runs.